Welcome to the Explainer. Today, we are going to crack open the blueprint for these massive, multi-core computer systems. I'm talking about the really big ones.
So what really separates your everyday laptop from a beast of a supercomputer? I'll give you a hint. It's not just about having more cores. It's really about the incredibly clever, kind of genius set of rules and the infrastructure that keeps all those processors from, well, tripping over each other. All right, let's dive right in.
Okay, so let's start with the big one, the core challenge that pops up the second you try to scale beyond just a handful of processors.
You see, as you start adding more and more of these processor cores, they all need to talk to the same shared memory. And, well, that can lead to some serious chaos. Think of it like a huge traffic jam.
So that brings us to the fundamental question, right? How in the world do you keep hundreds of processors from basically writing over each other's work and corrupting all the shared data? The goal here is to make sure every single processor sees a consistent, correct view of the memory. This whole idea, this holy grail, is what we call cache coherence.
All right, so to solve this massive traffic jam problem, engineers came up with a really elegant system. Instead of a chaotic, free-for-all intersection, think of it more like a super well-organized library.
And what's really fascinating is how the strategy for this evolved. Early on, systems used something called a Snoopy protocol. It's pretty much exactly what it sounds like. Every time a processor changed some data, it would just shout about it to every other processor. Now, for a handful of cores, that's fine. But imagine hundreds of them all shouting at once. It's a total bottleneck. The solution? This much smarter, targeted, directory-based approach.
So instead of that broadcast storm, a processor just asks the directory. It sends a simple request, and the directory, our digital librarian, knows exactly who has a copy of that data and who needs to be told about the change. It's like using a scalpel instead of a sledgehammer, just pure surgical precision.
And it turns out there are a couple of main flavors of this. On one hand, you can store all that directory info right there with the data in main memory. It's pretty simple, it scales well, but yeah, it does take up extra space. The other option is to distribute the directory across the caches themselves. This is great because it saves memory, but as you can probably guess, it gets a whole lot more complex to manage.
Okay, so tracking who has what data is a huge step, but it's not the whole story, not even close. All those processors also have to agree on the order in which things happened, and that brings us to the official rules of engagement for shared memory.
This is what we call the memory consistency model. Think of it as a contract, a deal between the programmer and the system. It's the official rulebook that defines how memory operations are going to appear to execute. And you absolutely need this, because without it, your program could spit out different results every single time you run it. Total nightmare fuel for any programmer.
Now, the granddaddy of all of these models is called sequential consistency. It was defined by the absolute legend Leslie Lamport. And the idea is actually pretty simple, but it's incredibly powerful. It says that even though everything's happening at once, in parallel, the final result has to look like there was some single, logical, sequential order to all the operations.
All right, let's make this real with a classic example. Picture this. You've got two processors. Processor 1 writes a 1 to a variable x. At the same time, processor 2 writes a 1 to a variable y. Then, a little later, they swap. Processor 1 reads y, and processor 2 reads x. To start, let's just assume both x and y are 0. So what can happen here? Well, it's possible one processor sees the update and the other doesn't, or both see the updates. But here's the crucial part. Under sequential consistency, it is absolutely impossible for both processors to read the old value of 0. Why? Well, think about it. For that to happen, both reads would have had to finish before either write became visible. And that breaks the rule. There has to be some valid sequential ordering of events. And in any valid order, at least one of the writes has to come before one of the reads. So at least one processor must see the other's update. Okay, so we've got rules for our data, and we've got rules for the ordering of operations. What's next? Well, now we need the actual tools that let processors coordinate their actions without, stepping on each other's toes. And that's where synchronization comes in. It's all about managing who gets to access shared stuff and when. It's basically a digital traffic cop. This is the magic that prevents, say, two processors from trying to update your bank account balance at the exact same millisecond. That would be bad.
Now, sync comes in a couple of main flavors. You've got point-to-point sync, which is like a direct handshake between two processors. One just signals to the other, hey, the data's ready. Then you have barrier sync. This is more like a group checkpoint. Imagine a whole team of processors working on a big job. They all have to reach the barrier and wait until every last one of them gets there before any of them can move on to the next phase.
So one of the coolest hardware tools we have for this is a special pair of instructions, load linked and store conditional. The easiest way to think about it is like a super careful atomic handshake.
Here's how this handshake works. First, the processor does a load linked. It reads a value, but it also kind of bookmarks that memory location. It puts a little watch on it. Then it goes off, does its calculations. When it's ready, it tries a store conditional to save the new value. And here's the magic part. That store will only succeed if no other processor has messed with that bookmarked location in the meantime. If the bookmark was disturbed, the store fails, and the processor just knows to try the whole thing over again. It's a really clever way to make sure an update happens all at once or not at all, without needing slow, traditional locks.
All right, we're almost there. We have the librarian, we have the rulebook, we have the handshakes. But there's one last piece of the puzzle. How does all this communication physically happen? This brings us right down to the foundation of the system itself. And that foundation is the interconnection network. You can think of it as the computer's nervous system, or maybe its highway system. The way everything, the processors, the memory, is physically wired together has a huge impact on performance, scalability, and of course, cost.
So this physical layout, or what we call the topology, can look a lot of different ways. You could have a simple bus, which is basically one shared road for everyone. It's cheap, but yeah, it gets clogged up fast. Or you could have a mesh, which is more like a city street grid with lots more paths. For the really big, massive systems, you might even see something like a hypercube, a super complex, multidimensional structure that honestly scales incredibly well.
And hey, just like a real highway system, you can't just have roads. You need routing algorithms, like a GPS, to choose the best path for all the data to travel. And you absolutely need flow control to act as traffic management, to prevent total gridlock when things get super busy.
And look, this isn't just theory. These are the principles that built the supercomputers we used to dream about. We're talking about real-world systems like the SGI Origin 2000. It had a hypercube network, and Sequence's NOMA Q. They used these exact concepts to scale up to hundreds and hundreds of processors, and they really did pave the way for the incredible machines we have today.
So there you have it. The next time you hear about a massive supercomputer, you'll know the real secret. It's not just about cramming in more cores. It's this elegant harmony, this dance of directories, consistency models, and network interconnects that allows them all to work as one. It really makes you wonder, doesn't it? What new rules, what new secrets will we need to discover for the million-core computers of tomorrow?